welcome to RAS session. And I'm with Linar assignee in Linar Lecting from Red Hat. I'm in the following 25 minutes, or maybe not, because we just have 15, maybe. So I will introduce the RAS architecture on ARM64-bit and based on the ARM RAS Extension, SDEI, and the APEI. So RAS on ARM64-bit is not a new topic. We had the similar session in the last Connect, but at that time we didn't introduce RAS. Let's move on. First of all, I will just introduce the RAS very quickly what it is, and just I guess most of people in this room know what it is, just very quickly. Secondly, I will talk about the new extension in ARM-VA.2, which provide a better support for RAS. Then I will simply present a new interface between OS and firmware called SDEI, which is a new interface like PSEI. We'll also review the 4 APEI table. So after all this introduction, I will put everything together, give example of the use case based on the RAS extension. So let's do it. So what is RAS? RAS is reliability, availability, serviceability. So we know these three words measure that if a system can live long and corrected and maintainable. So what does RAS function do in a system? It can detect and correct the error before they cause the application or system failure. Then following all component can be predicted, and identification, and it allowed replacement during the schedule maintenance. But the key point here is RAS architecture only cared about error from hardware. We just cared about the hardware error. So software error is for debugging, right? We need to debug it. So why it is so important? Because our enterprise system is large, right? It's running a very critical mission, and so the damaged part, or maybe like the broken thing, will be showed up maybe every several days. So every several days you can, this thing is broken. So we cannot avoid it, but we have to maintain it. How to make this cost, maintain the cost down? So we need RAS to predict it, to replace the failing part of the system. So, but do we have plan B? So if we don't have RAS, what we can do, right? So we can pray, right? We can say, okay, God bless my whole system. And in Chinese we say Aumi Tofo right before vacation and holiday, right? You can do this. And if you do so, I will say, okay, may the luck be with you. So before we move to the RAS on x86, we just have review the RAS on x86. So we have MCA is machine check architecture on x86. Sorry for this, because I downloaded, so the format is a little messed up. In this architecture, we have the register, we have the exception to make the application know where is the problem and log the error. But it's x86 specific, right? So, except this, we also have some generic way to get error information like EDAC, also like AER on PCIe. For memory control, we have ECC, which is a hardware feature. On x86, we already use APEI, but nowhere violate because you know, especially for BRT table or some other table, we are still upstreaming, even it has been showed up for several years. So that's the overview of RAS function for different layer of the software and hardware. For the hardware, we can do the fault prevent, detection, and correction. And then once the hardware cannot handle this, we use firmware to collect error info and also do some fault handling if it can do that. If firmware cannot recover from fault, we can use OS to recover the error and report error to the application. And in the user space, we use rasdaemon to record all the error info and also maybe do some analysis for error because we want to predict the failing part of the system. So on ARM VA, especially for ARM VA.2, we have some requirement for RAS. First of all, CPU, we need EL2, EL3, maybe one of them, maybe both. And we also need GIC. It's interrupt control. It also can be some other kind of interrupt control, but it has to be it has to include some feature like routing and PPI, SPI, or maybe priority and grouping, something like this. But most importantly, on VA.2, we have RAS extension. It falls into three parts. ESB is a new instruction to synchronize the unrecoverable error, and we use a poisoning mechanism. It's a hardware mechanism to let the producer and consumer know there is an error. And we also have a whole bunch of register. We let firmware to collect the info, control the exception, interrupter, and let the kernel or OS know where is the problem or how to handle this. So the RAS extension include these three parts. So that's a little complicated because in the RAS system, we need to know what kind of error we are facing. So that's the map I dropped for according to the RAS extension documentation. So most importantly, I think we need to understand what is the default error. So this error is has something to do with the new instruction where I just say ESB, that instruction. So other than that, so before we move on, just this map it's a little complicated. It will took some time. So I will not just I will just move on for this. And if people interested about that, I can send you a big picture of that. So the ESB is a new instruction. Is one of the important part of a RAS extension. By the help of the ESB, software can isolate the location of error between the ESB and the previous ESB instruction. It can be used in OS when the ESB is execute if the SEI, which is handle SEI, which is used for reporting the asynchronous error, which is unmarked, SEI will be generated. Otherwise, the info of error exception will be pending in the DISR. So the VDISR is totally for virtualization. So in one word, ESB is for asynchronous error. So we have a whole bunch of register. Sorry, so we have each node has some group of register to record error to control for handling interrupter, recurring interrupter, or exception. So we have system view register, system register view. Also have memory map register view. Most of the time, we will just use the memory map system view in firmware. So let's this slide just this slide is just show the possible connector of interrupter and exception of RAS node in a system. The synchronous asynchronous error exception will be directly looked to the synchronous exception and SEI of the on-call. Then the error recovery interrupter and the fault handle interrupter will be route to the GIC or the onboard RAS controller. For a RAS node, it may have all these interrupter and exception, but which one will be used or how to use them decided by firmware. I mean, ARM trust firmware, UEFI, and ACPI. They will cooperate together and let kernel know how to handle the error. So now we have talked about hardware support of RAS. So let's move to the software part. On ARM64, we plan to use a firmware first mechanism, but OS has also can decide which system event it want to handle or which it will be just ignored. So SDEI is a PSCI-like interface for register and serving the system event, which come from system firmware. But it's not just for RAS, it's also can used in debugging. So let's just show some function in SDEI. Through this, you can understand what is the SDEI. Just handle some event and control the interrupter, right? So it's this interface is under development. Those will be changed in the future. It's not we haven't released the documentation, but I think it will be soon. We hope so. So after this, so we now went through the hardware and OS firmware control interface. Now we can quickly go through the APEI topic because we have the same slide, almost the same slide in the last Connect, right? SDEI is APEI provide a means for the platform to pass the error information from firmware to OS. We have 4 different tables for in the APEI. The first one is BUD. It's used for record error in the emergency, like the OS shutdown, and that means the OS cannot work. So the firmware maybe firmware need to reboot the system, and this reboot is a wrong reboot. So the system, the error information is still in the register. So once the system back online, the firmware will collect the information from the RAS extension and pass the information into the OS in the boot time. So that's the scenario and mechanism for this. The key info being held in this table is where is the error and how the size of the record region. And so once we have this error, so what is the format for the error block, error data, right? So the error block is formatted by firmware in CPER format. This is described in the UEFI spec. From this structure of CPER, you may see that we can report all kinds of error. We can think of. That's the advantage of APEI and CPER. So you can see we have x86 ARM code and also firmware error. For all kinds of error we can have. So that's an advantage, right? The second table is at HEST, which is used to record a runtime error. We can use this table to let kernel know how to handle the runtime error, and it provides a key info about once error occurred, how the firmware trigger OS, where is the error record, and how to release the memory of record. So in this table, we have several subtable to different kind of subtable to pass the information about error source. So for ARM64, we only cared most of the time we cared about the GSESV2. We will use this structure to pass the error source info to OS. The rest of 2 table is ERST and EINJ. So ERST is the operation abstractor which provide the necessary information to communicate with onboard persistent storage for error recording. And EINJ is also an operation extractor which provide a generic interface. Then OS can inject a fake hardware error for RAS testing. The possible use case is using the system FS interface to talk to EING driver, and the driver a driver already get necessary information in the boot time, and the driver know how to talk to the vendor-specific register for RAS testing. This register won't be released or won't be published. The information won't be published to outside the chip vendor. Just only the RAS, maybe just RAS, maybe just firmware engineer know how to use that. Just this information will be keep in the firmware. So now we have all the component of we have introduced all the necessary info of RAS on ARM64. So let's just put them together, and the following slide will let you know how to what is the workflow once error occurred. So for BRT, once the system has a fatal error, the system will totally shut down, right? The OS has crashed down, so the firmware will get information, say, okay, the system shut down, we need to reboot. So maybe it's the virtual machine, so we need to reboot. But all the information still keep in the register. So once the ARM trust firmware back online, it will collect all the information from error register and pass it to the print K. You just use the print K to print the error in the message. So that's the BUD. But something we haven't finished is we can print this in the message, but we still cannot save it in somewhere. So maybe in the future we need to make rasdaemon to do this job. Maybe we need to make BUD driver to save this information to some other place. So let's make the future work. So once we get an error in a runtime, we may, the hardware, the error occurred in a runtime. So ARM trust firmware is notified. It is informed by the interrupter or exception. So the firmware will create the error board by error data by the info from RAS extension register. And then ARM trust firmware called the error recovery handle, which handle has been registered in the boot time by the SDEI interface. So that's the whole picture of that. And so and then by the help of the error recovery handle, we can get the information and pass the information to the RAS to the user space. Maybe we can use RAS event. Maybe we can use a RAS event, and rasdaemon can get information from RAS event. So store the information to somewhere. So in this scenario, some part of the software still under development, especially like the GHESV2. Qualcomm engineer is upstream the GHESV2 support. Right now, the latest support is V11, I guess. So that's the current state of development of RAS. We have the ARM v8.2 spec include RAS extension, and firmware for the firmware side, RAS extension documentation describe different different scenario in the error in the system. So some kind of error, different scenario in this. So we also, but this RAS extension also under development. And SDEI is under development. For the OS, APEI on ARM64 has been enabled in the kernel. The enablement patch has been accepted, I guess, nearly more than half years. And the BRT's work, I have tested on foundation model. You know, the GIC v2 is upstreaming, and but the rest of the two table, we still, you know, we don't have the firmware to do this. So we need, it's operation abstractor, so we need a firmware to support it. We cannot test it right now. For daemon, the rasdaemon can be launched on ARM64. So the future, what we are missing, and we are planning to do on what we are planning to do on RAS architecture. We actually we need real hardware right now, and we also maybe even a simulator will be good, but we don't have this, so it's missing. From the firmware side, RAS extension and SDEI spec are under development. So we hope this spec can be released as soon as possible, and at least give the chip vendor a guideline how to design the chip. But without this, we really cannot move forward. So we also need a untrusted firmware RAS extension support and SDEI distributor in the firmware. And in the OS, we also need to implement SDEI client and distributor. The distributor is for virtual SDEI interface. So I guess that's all the thing I have. Any question?
Any plan for error recovery and error isolation in OS?
Sorry?
Any plan for error recovery and error isolation, something like that?
We haven't. We are planning to do this, but we don't have a resource to do that. We don't have a hardware, and for the RAS extension spec, you know, we have this mechanism, but we still need a real release guideline, real release documentation to do that, to planning this.
So does SDEI is that only applicable if the RAS extensions are implemented? Are those tightly tied together?
No. It's
so
not just for RAS.
Independent. I mean, obviously get more isolation and stuff with RAS extensions, but okay, so it's still applicable for systems without 8.2 functional.
If anything, it makes more sense there because before 8.2, you can only really do RAS firmware first.
Right.
After 8.2 opens the notion of kernel first because there is a RAS architecture. Before 8.2, there isn't a RAS architecture.
So, any question? If not, we can move to the next topic. Thank you.